Alrighty, folks. So we now move on to chapter 9, which is estimating the value of a parameter, which the entire course has kind of been building up to this second half of this semester. A lot of what we've done so far lays the groundwork for these chapters coming up, starting with chapter 9. And let me try to give you the point of where we're going with this. So let's go back to day 1 when I asked how much does the average CCBC student weigh? And we all agreed on that first day of class that we can't go out there and weigh every CCBC student, putting them on a scale, measuring it ourselves, and then averaging them all out. That's just not feasible. I don't think anyone can do that, no matter how high they rank in the college. So we all kind of agreed that we had to resort to statistics, right? So just to remind everyone, our goal was the parameter. In this case, it was the average weight, so it was mu. And what we could use, what we could find, however you want to put it, was the statistic. I shouldn't say the statistic, maybe I should say a statistic, right? I go out there and I find a statistic. I go out and sample let's say maybe sample 100 students. And then find their average weight. And if I find that average weight of maybe, let's say 100 students, could be 500. I don't know how many students I want to actually sample. Depends on, I guess, the problem, right? But let's say I maybe sample 100 students, find their average weight. What would I do then? Hope it's close to the parameter. Hope it's close to the true average CCBC student weight. But it might not be, right? Like the true average CCBC student's weight, whatever the true average is, let's say the true average, I don't know, let's say 170 pounds. My statistic that I find, let's say I go out there and sample 100, what if I find 168 pounds as the true statistic? But that's pretty close to the true average, right? But we know that it's completely dependent on who those 100 students I weighed was, right? Another statistic that could have been found was 176 pounds, maybe a little too much. Another statistic that could have been found, say you go out there and sample people, and you find 167 pounds. So these statistics, we hope each individual, me and those two other people, would hope that it's close to the parameter. Right? That's kind of what the course was based off of, right? We wanted to know the value of the parameter, but a lot of times it's either too expensive or too difficult to find, so we go to the statistics and see what they say. And you can see the statistics I came up with, 170 being the true value of a parameter would not be surprising. The true average CCBC student weighing 170 pounds wouldn't be surprising considering 3 different statisticians found 168, 176, 167. They're all kind of close to the parameter. But we have to be careful because maybe another person says the average weight is 195 pounds. They got a lot of heavy people in their sample. That's going to happen sometimes. We just need to kind of deal with this. Deal with the fact that different samples produce different statistics, but we want the statistics to be able to say something about the parameter, right? So we want to kind of deal with the fact that there's some randomness in what the statistics are going to be, so that we can really accurately guess what the parameter's value is. And that is the whole point of the class, and that's what we're starting to do in this chapter. And we start, the first section we do is going to be 9.1, which is estimating the value of a population proportion. And I'm just going to draw your mind back to, I believe it was the last class we had when we did proportions. We talked about the distribution of sample proportions. Recall that proportion is denoted as, we have two ways to denote it. We have p hat or p. And what are the differences between those? Well, in statistics in general, the difference between notations is always going to be, this is the statistic version, right? This is what we found. And regular p, no hat, is the parameter. Just want to remind everyone, because I'm going to be using p hat and p separately. So p hats are the statistics that we find through samples. P with no hat is the true parameter. If I was able to go out there and get the data on every single person or thing in my population, right? All right. Okay. So there's going to be a little bit of backstory before we get into some math. So let's start with an important definition. A point estimate is the value of a statistic that, I'm going to put in parentheses, hopefully, hopefully estimates the value of a parameter. All right, and just a quick example. Find the point estimate for the proportion of Americans that smoke tobacco. If you find in a random sample of, let's keep it very simple, not too big. If you find in a random sample of, let's say 164 Americans, how many did we find smoking? Let's say 23 smoke tobacco. So you went out there and you sampled 164 Americans, and out of those, you found 23 smoke tobacco, and we want to find the point estimate. Well, knowing that a point estimate is the value of a statistic that hopefully estimates the value of a parameter, we know that even though we only sampled 164 people, that's definitely fewer than, all Americans out there, right? That's not everyone, so this is definitely a sample. So what we found, I'm using p hat as my statistic because it's a proportion and it's from a sample. We found my p hat. We found 23 out of 164 say they smoke, and using our calculator, that means that we have 0.14, that actually kind of rounds exactly to 0.14 as the proportion of Americans that smoke tobacco. So my point estimate is just that. It's what I found from my sample. I found about 14% of Americans smoke tobacco. Now, I don't know why that's still there. What is that? Oh, there, it went away. Sorry guys, my first time using this software, so I don't know what that bubble was that was there. Anyway, back to the statistics of it. Let's see. Point estimate is the value of a statistic that hopefully estimates the value of a parameter. So we went out, we sampled 164 Americans. We're guessing, well, we found that 14% of them smoke. So my best guess for the percent of all Americans that smoke would be that 14%. I don't have anything else to go off of. This would be my best guess. So that is my best guess for the true parameters value, right? My sample, my statistic was 14%. So my best guess for all Americans is about 14%. I don't have any other info to go off of. All right. And like I started this video with, we realized that point estimate of 14% of people are smokers will be different depending on who's doing the sampling, right? So let's say, I'll keep it black. Let's say, I don't know, I'm going to make someone's name up. Joe samples. How many did I say? I sample? Let's keep it consistent, right? Joe samples 164 Americans and finds, let's see, what's a good number? Finds 21 smoke tobacco. His point estimate is then his p hat is actually different than mine, right? He found 21 out of his 164. He obviously sampled different people than I did. Would be 21 over 164. And 21 divided by 164, according to the calculator, is about 0.128. And then let's say Jane samples 164 Americans. And her p hat is equal to, I don't know, maybe she got a lot of smokers in her sample, maybe 17.2%. Oh, actually, maybe I should be consistent. I shouldn't report hers as percentage when I reported the rest of ours in decimal form, right? It should be consistent. I should be a good teacher. Maybe Jane found 0.174 as her proportion. And so the three of us went out and sampled 164 Americans. I don't know why I chose that number, but I found 14% of people smoke. Joe found, let's undo that. Joe found about a little less than 13%, so 12.8%. And Jane found 17.4%, right? We all found different percentages. We all have different point estimates, different proportions, however you want to say it. We all have different ones because that's statistics for you, right? It depends on who those 164 people we get in our sample and whether they're smokers or not. There's some randomness in it. And all three of us are going to be hoping that we got close to the true proportion. I don't know what the true proportion of Americans that smoke is. That's going to be really difficult to find out. You have to go out there and sample all couple 100 million Americans. That's pretty tough, pretty expensive, going to take a long time. But we see, all right, 14%, maybe 13% almost. This is about 17.5%. We're going to guess it's somewhere around those. Each of us, me, Joe, and Jane, would all be pretty confident, hopefully, that we got something close to what the true proportion is, because that is still what we don't know. We don't know the true proportion of Americans that smoke. Oops, that smoke. I could probably clean that up a bit. We don't know it, right? Each of us have our own best guess. We have our own point estimates, but who's right? Maybe none of us, right? So that's what this section deals with, is how do we know what the true proportion is? Well, spoiler alert, we will never actually know the true proportion, but we can basically enhance our guesses by constructing intervals. So here's another definition, a confidence interval. For an unknown parameter, consists of an interval of numbers based on a point estimate. Okay, so what we're going to be doing is constructing an interval that hopefully will capture our true parameter. So, oops, let's see, the level of confidence. And in parentheses, I'm going to let you guys know which is set at the start of the problem. Represents the expected proportion of intervals that will contain the true proportion, which means the parameter, right? We're going to have to figure out how to construct these confidence intervals with math in a little bit. But for now, let's talk about the common levels of confidence. Still not on the math yet, still doing some vocabulary. But some common levels of confidence that I've seen are 80, 85, 90, 95, 99, and 99.9, and those are all percentages. These are some common levels of confidence you would see in real life, and specifically 95 is the big one. That's everywhere. You'll see that in a lot of places. At my job, we use 90% confidence intervals. Sometimes you'll see 99, especially if circumstances want you to be a little bit more safe. You know, how confident are you that this drug won't kill me? I'm going to want you up here. pretty confident. But these are some common levels of confidence that you'll see in real life and in our examples in class. These common levels of confidence aren't a catch-all, though. If you want to be weird, if somebody wants to, they can construct or they can have a level of confidence of something like 91%. I mean, there's nothing preventing you from doing that, but it's just not normal to. Like I said, these are the most common, probably because they're nice round numbers, pretty high, right? 80, 85, 90, 95, 99, 99.9%. You can be weird, do something like 73% if you want to, but that's not really used much in real life. With the levels of confidence comes something called a significance level, which I'm going to define now. The book doesn't really do it, but they throw a symbol at you without really letting you know what it means. So let's do that. The significance level denoted alpha, it's a Greek letter again, denoted alpha, is the, let's say, complement of the given confidence level. For example, find the significance level alpha for a confidence level of 95%. Well, I say complement because I want you to think P's and Q's. We've gotten really good about coming up with Q if I give you P. That's the same thing going on here. When I say the significance level alpha is the complement of the confidence level, the significance level alpha we would get by doing 100% minus 95%. So the significance level for a confidence level of 95% is 5%. So confidence level of 95 means significance level of 5. And I mean, you know me, right? I would prefer this as a decimal. I don't really like dealing with percentages. So you can even skip the percentage step, right? Just do 1 minus 0.95, right? And that's 0.05. So the significance level for a confidence level of 95% is 0.05. So if you hear me say a confidence level of, let's say, 99%, then your significance level would be what? 1%, right? So you might hear me start talking about significance levels. You're going to hear me talk about them more when we do hypothesis testing, but I just want to keep everyone in the know because the book does start to use this alpha symbol, this thing right here. Just know that it's basically the opposite of your confidence level, right? Okay. So, further expanding on this confidence level idea, what did it say? The level of confidence represents the expected proportion of intervals that will contain the parameter. And these intervals, we're hoping do, but we're only going to be so confident. We're not going to be able to construct an interval that we're going to be able to say, for sure, 100% confident, this has the true value of the parameter in it. That's just not going to happen, no matter how good my sample is. So, going back and looking at these 3 point estimates me, Joe, and Jane found, sorry about the unoriginal names, but me, Joe, and Jane found these different levels of, these different point estimates. We're going to construct intervals with a certain level of confidence that hopefully contain the true parameter. And I'm not going to do actual math yet, but let's say here's our intervals, our confidence intervals. And let's say we were 95% confident. And let me see what the colors were. So my point estimate was about 14% because I found the 23 out of my 164 smoked tobacco, right? And sorry for all the scrolling. I wish there was a better way to do this. Oh, there is. Thanks for hanging in there, guys. I'm learning this as you guys are. But let's see. I found 23 out of the 164. That my point estimate was 14%. And let's say my confidence interval, back to taking notes. Since I get my point estimate was 14%, maybe my confidence interval is between 12% and 16% smoke. So again, I'll get to how this actually is calculated in a little bit, but I want to make sure that we understand why we're doing this. But I found 14% in my sample, and then through some math magic, I report that between, I think I used orange for me, between 12 and 16% smoke. And then these other people, these other statisticians, could also come up with their ranges. So Joe found about 13%, right? 12.8% of people smoke. Maybe he says in his report between 11 and 15% smoke. And Jane, let's see, what did she have? 17.4. She had a lot of smokers in her sample. She says, sorry, 17.4. Maybe she says between 15% and, let's be consistent here. She says maybe between 15 and 19% of people smoke. All right, so we're going to do this math magic to come up with these intervals in a little bit. Don't worry just yet. Let's see, I used green for him. And I think I used blue for her. But you'll see, like, since we all got different estimates, we're actually going to end up with different intervals themselves. But since this whole thing is set up to be 95% confident in these ranges, what that means is that the true parameter out there, so the true proportion of smokers, let's say, is 15%. And I'm going to highlight this red because in real life we don't know this, right? We don't know what the true proportion of smokers is. But if we were to plot these different ranges each of these statisticians are giving, I said between 12 and 16, Joe between 11 and 15, Jane between 15 and 19. That if I were to like plot these ranges so that you can see them, maybe here's me. This is 16%. My lower limit was 12%. I said between 12 and 16. Joe said it could go a little lower, maybe as low as 11 and as high as 15, so right there. And Jane said it was actually between 15 and 19. How much is that? Let's see, it's 2 each. So maybe up here. These were the different ranges we all came up with based on our individual samples. My range is right here. This is where I believe the true percentage of smokers is. Joe believes it's down here. Jane believes it's up here. None of us are really going to know what's right, but the math says that if we knew the true proportion of smokers, which it says is 15, that if we were to repeat this process a bunch of times, not just me, Joe, and Jane, but a bunch of other people, that 95% of these ranges, 95% of them are actually going to hit or contain that true proportion. Remember, we don't know what that true proportion is in real life. But since we're all constructing ranges, a lot of us are going to be confident that it's within that range. And actually, in this case, my 3 little mini examples, all of us actually hit it. Jane hits it on the lower side. Joe hits it on the upper side. I got it a little on the high side, but still within it, right? Right there, right there, right there. So we actually, all 3 of us have it in our ranges. But we wouldn't know that in real life. We wouldn't know that this 15% is true. It might not be, I haven't researched this at all. But that's the gist of it, is that if we construct a bunch of confidence intervals, a bunch of different statisticians, a bunch of different samples of the same size, that 95% of the intervals we're going to construct will actually contain the true proportion. And that does not mean that if we construct an interval, it's a 95% chance that it's in it. It's a 95% proportion of intervals, if we keep repeating this process, that will contain it. Because let's say we had a 4th person, I don't know, and they said the range was like this. They're still 95% confident in their range, but in actuality, they missed the actual target, right? They didn't actually capture the true proportion. But again, they wouldn't know that. In real life, they would say, I think it's between here and here, not knowing that the true proportion actually is outside their range. They're still pretty confident in this range themselves because they don't know the true proportion. But if you repeat this process a bunch of times, most of your confidence intervals, 95% in this case, will contain the true proportion. And I hope that is clear. All right. So how do we actually construct these intervals? How did I get these ranges? Me, Joe, and James, and this other person. How did we actually come up with them? Well, there's some math, and unfortunately or fortunately, it involves a lot of what we've done up until this point. In general, make sure I have this right. In general, to construct a confidence interval, we take our point estimate that we got from our sample. Remember the point estimate, I said it all the way at the top. A point estimate is the value of a statistic that hopefully estimates the value of a parameter. It's what we find in our sample, right? It's what we find. It's our best estimate. So in general, to construct a confidence interval, we take our point estimate, we take that best guess we have, and we add and subtract something called a margin of error. Okay, so what is a margin of error, right? The margin of error for proportions. And a lot of times, margin of error, you'll see me denote it ME a lot, because I don't feel like writing margin of error a bunch. Margin of error for proportions is equal to Z sub alpha over 2 times square root P hat Q hat over N. And just so that you guys can see it, I'm going to zoom in a little bit. Z sub alpha over 2, this is why I introduced that alpha symbol above. It has to do with our significance level. And I don't know if you guys remember, but I mentioned it in class before that my Z's, I always make sure to put a slash through them, and the 2's I write don't, because my handwriting, it's hard to tell my Z's and 2's if I don't do that. So this is a Z, the last letter of the alphabet. This is the number 2. So it's Z and then a subscript alpha divide by 2 times this square root, big square root, right? Big square root P hat Q hat over N. All right. This square root symbol actually should be pretty familiar to you guys already. I'm going to hold off on letting you guys know what that Z thing is yet. Let's talk about the square root. The square root P hat Q hat over N is called the standard error. In layman's terms, this standard error is kind of like a standard deviation, and it should look familiar to you because last class, when we were doing sampling distributions for proportions, I had the standard deviation on a normal model being square root P, Q over N, assuming we knew P, Q, and N. And you see how it's basically the same thing, right? But instead of PQ over N, we have P hat Q hat over N. So we got hats this time because we're basing it on a statistic. And so a lot of times you'll see me, and it might be bad math, you'll see me write the margin of error as this Z sub alpha over 2 times a standard deviation. And that's me being lazy, not writing the square root. And it's actually probably bad notation, but I got into the habit of that because it's so much like the standard deviation for proportions from last class. And I'm not going to take off if you do this too, because it actually helps me remember that the standard error is sort of like a standard deviation. That's why they both have the word standard in it. But yeah, this P hat Q hat over N is a lot like what we did in the last class we had. All right. So that is the standard error. Now what about this other funky thing, right? So this Z sub alpha over 2, the Z, I say sub meaning subscript, alpha over 2, is called the critical value. And the critical value depends on the level of confidence set at the start of the problem. So your critical value is going to depend on the confidence level set at the start of the problem. So the critical value for 99% confidence interval is going to be different than the critical value for a 95% confidence interval, which is going to be different from 80%, whatever, 73% if you want to be one of those weirdos that creates a 73% confidence interval. Those critical values are going to be different for the different levels of confidence out there. And what are the critical values? For different levels of confidence? All right, we have good news and bad news. I'll do the bad news first. Get that out of the way. Finding the level, the critical values is kind of tedious. That'll be the bad news, and I'll show you how right now. Find the critical value for a 95% confidence interval for proportions. So just bear with me as I do this. But from what we know from the previous section is that proportions follow the distribution of proportions, sample proportions, follows a normal distribution. And so I'm going to draw my picture of that normal curve. Oh, that's bad. That is not great. Let me try that again. Let's see. That's better. Not great. I'm on an iPad here. Cut me some slack. But we have our normal distribution. And we know, let's say we're going to label our z-scores here. We know a z-score of 0 is in the middle, right? And it goes out 1, 2, 3, -1, -2, -3, yada, yada, yada. These are my z-scores on the standard normal distribution. And if I want to find a critical value for 95% confidence interval, what that's going to do, I'm going to try to break it down kind of like in a picture form, is we need to reserve, ooh, that is not what I wanted to do. We need to reserve 95% of this picture for our interval range. And we need to know what z-score on both sides will leave a chunk of 95% between them. And so that's going to leave 5% on both sides, which is, oops, undo that. Which is going to leave 2.5% of the picture on both sides. This is usually where I start to lose people. Let's see, let me highlight things. So if we have a 95% confidence interval, knowing that we're on the normal distribution because of last section, that means we're leaving a 95% chunk in the middle for our interval because we want to be 95% confident. That leaves 5% to be split out on both sides, which if you have 5% split out on both sides, that's 2.5% on either side. So my confidence level from the problem said 95%, which means our significance level is 5%, which I mentioned that earlier, right? Yeah, back up here I said for 95% confidence level, significance level is 5%. So 95% confident, and then the extra 5% we're going to split out on the other two sides. We need to know what z-scores is going to separate it so that 2.5% is below some z-score here, 2.5% is above some z-score here, which leaves 95% in the middle. And the way we do this is using that z-chart, standard normal chart, in reverse. And this is why it's kind of painful, is because normally we have a z-score and we look it up on the chart to get a probability or a percentage, right? This is what we get from the chart. We take a z-score, we look it up, we get a probability or percent. Now we know what the percentages are. We need to go back and find what z-scores achieve that. And it's always better to do it on the negative side. I'm going to redraw my picture. We're reserving 95% for here, 2.5% on either side. And we need to know what this z-score is that is going to achieve this kind of picture. And we're going to use the z-chart in reverse, which means this percent right here, these ones, we need to look up inside the chart, not along the edges like we're used to. And this is a math class, so we don't deal with percentages, right? 2.5% is 0.0250. I'm just converting this percentage right here into decimal. So we look inside. the z-chart for as close to 0.0250 as we can get. And let me get my z-chart ready right here. Let's see. So if you're looking on the z-chart and you want to get as close to 0.025 inside the chart, remember, we're looking inside at the big table of numbers. We're not looking along the edges anymore. If we look inside and you look on the negative side, we have, let's see, look on the negative side near, let's see, negative 1.9. Yeah, look at the row for negative 1.9. So on the z-chart, you have 1.9 along the edge, negative 1.9 on the edge, and I'm going to start listing them out as best as I can here. Under the 0.0 for negative 1.9, it starts out 0.0287. Under 0.01, it has 0.0281. Under 0.02, so negative 1.92 has a chart value of 0.02 what? 74. So I'm just trying to point you out to the chart. 0.03, 0.04, 0.05, 0.06 is all we're going to need. Under 0.03, we have 0.027. Nope. It's 668. 0.04 is 0.0267, 0.0267. 0.05 is a value of, I'm just copying the z-chart here since there's no easy way to map it into the iPad. Whoops. Reset. Let's separate them too, keep things straight. Under negative 1.95, it's 0.0256. Oops. I don't know why I did that. 56. And under negative 1.96, it's 0.0250. And that, ladies and gentlemen, is exactly what we want. We wanted to find the z-score that achieved 2.5% below it. And that is, apparently, the z-score that achieves that is negative 1.96. And you can check me out, but if you go on the positive side and look up positive 1.96, that'll leave 2.5% above it. You can go and verify that on your own. And critical values always will use positive. It actually ends up not mattering anyway later, but in general, we're going to use a positive critical value. So the positive critical value for 95% confidence interval is 1.96 for these reasons here. This critical value is found by putting the level of confidence in our normal curve, leaving 5% left over to be split out on both sides, right? This is 5% total left split out on both sides. And the z-score in the chart that leaves 2.5% below and 2.5% above is negative 1.96. And we see that by looking inside the chart for as close to that 2.5% as possible, which it actually gets it exactly at negative 1.96, which means our critical value is 1.96. And like I said, you can leave it negative if you want. It's not going to hurt anything, but for some reason we like keeping everything positive. Now, I said we have some good news and bad news earlier on calculating these critical values. And I said the bad news is it's tedious because we have to use this chart in reverse. It's not fun. So hopefully you've been waiting for the good news. And the good news is you're not going to have to do this. I'm not going to be so cruel. So everything after, like coming up with this, using the chart in reverse, you're not going to have to do. It's just kind of for your knowledge on where these critical values come from. So here's your example of where it comes from. So how are you going to get your critical values if you don't have to do this whole weird method? Well, I'm going to give them to you. If you look on your formula sheet that I provided in class, and it's also on Blackboard. Let me pull mine up real quick. On your formula sheet, sorry, it's taking a second to load. On your formula sheets, sorry, computer's being real slow, probably because I'm recording the lecture too at the same time. There we go. On your formula sheet, you actually have something underneath proportions, and it says confidence interval, critical values, and it has some common ones there, 80%. This is on your formula sheet. It says the 80% confidence level, the critical value is 1.28. 90% confidence level, the critical value is 1.645. 95% confidence is the 1.96 we already came up with in my example above. And the 99% confidence interval critical value is 2.575 for its critical value. So these are the confidence levels and their critical values. So all you're going to have to do is look it up on the formula sheet, what's your critical value. But just in case any of you go on to another statistics class or you have to retake it with another instructor or something, this is how the critical values are found, is this whole using the z-chart in reverse. But don't worry if it didn't really make too much sense, this whole part right here that I'm highlighting yellow, maybe make sure, let's see, I'm gonna have to highlight that something else now because that was the answer, right? Everything right there that I just highlighted yellow, all this stuff up here, you don't really need to know how to do because you're gonna have a formula sheet that kind of maps the confidence levels with the critical values you need. Okay. Hopefully everyone's hanging in there. Not too lost yet. Who knows? Now we can actually start constructing our interval. Believe it or not, we're ready. So let me go back, let me recap. Let's see, the steps. Let me zoom in. Steps. Oops. To constructing a confidence interval for proportions. Step 1, find your point estimate. Step 2, after you find your point estimate, find your critical value. Step 3 is find your standard error. Step 4, find the interval. Take p hat plus or minus critical value times standard error. In step 5, write a statement. Oops. And those are your steps to constructing confidence interval for proportions. All right, so let's do an example. I don't know why sometimes it autocorrects my lines, my handwriting, to straight lines. Like I'm drawing a picture or something, I don't know. Example. All right, let's see. I'm going to try to use the book example. Going to cut out a lot of the fluff though. A survey of 800 teenagers. That drive found that 272 found that 272 admitted to texting while driving. Create a, let's do 90% confidence interval. For the proportion of teens that text and drive. Very dangerous stuff, right? All right, so following our steps, we need to find our p hat first, then find our critical value, find our standard error, create our interval by doing this plus or minus nonsense, and then write, ooh, look at that, write a statement. Can't believe I dropped the T crossing there. All right, so first step is find your p hat, and I'm going to label the steps. P hat. What did we find in our sample? Well, we found 272 of the teens out of the 800 admitted to texting while driving, right? And 272 divided by 800, I can't do that in my head. I'm going to need my calculator. 272 divided by 800 is 0.34. So about 34% of teens in the sample said that they text while driving. And a lot of times in the news, that's what they're going to put out. They're going to say 34% of teens admit to texting and driving. And then in the footnotes is where you're going to find this confidence interval. Or maybe somewhere else, maybe later, I don't know. Depends on the source. But a lot of times this is what's going to get reported. They're going to say 34%, and then a lot of times the confidence interval is kind of hidden somewhere else, but it's there. But we found 34% admitted to texting while driving. We realized that since we only talked to 800 teenagers, that it might be a little bit more, might be a little less. So what we're going to do is construct a range that we're pretty confident the true proportion actually falls within. So next step, find the critical value. This is going to be your easiest step, despite all that lecture earlier, using the chart in reverse. This is the easiest step because we just look it up on the formula sheet. Since we're doing a 90% confidence interval, looking it up on the formula sheet, a 90% confidence interval's critical value is 1.645, just from the formula sheet. If you want, you can do that whole using the z-chart in reverse if you want, but I'm going to guess most of you don't want to. And now we move on. Step 3, find your standard error, this square root p hat, q hat over n. Well, p hat is what we found, right? 34%. So 0.34 goes in for p hat times, what is q hat then? Hopefully you guys remember how to come up with the q's if you have the p's, but it's the complement, right? So p hat 34%, the leftover percent from the 100 goes into q, so 0.66. And n is total number sampled, which is our 800. It's our sample size, right? The biggest mistake here I'll find is some students will accidentally use the 272, but no, always remember your n is total number of observations. So 0.34 times 0.66 divided by 800, and keep in mind it's all underneath one big square root. That's another common issue, is sometimes people will type this into their calculator and accidentally end the square root after the 0.34, because some calculators will introduce a parenthesis first, and then some students will close it there, and that'll close the square root, but it's the whole thing is the square root, right? And so 0.34 times 0.66 divided by 800, all underneath one square root, gives me a margin of error, a standard error of 0.017, we'll say, after rounding. Step 4 said find p hat plus or minus z sub alpha over 2 times the square root pq over n. Okay, basically what the step 4 is combining these other three steps. Step 4, which is the p hat plus or minus the critical value times standard error, p hat q hat over n. Well, p hat was 0.34. I'm just filling in, what we found above, 0.34 plus or minus critical value 1.645 times the square root p hat q over n. Square root p hat q hat over n ended up being times 0.017. And since this is plus or minus, we need to do it both ways. When we do plus, that means we're taking 0.34 plus 1.645 times 0.017 and typing that into our calculator. Let's see, 0.34 plus 1.645 times 0.017 is 0.368, I guess we'll say. And if you change the operator to be minus, 0.34 minus 1.645 times 0.017. If you change that middle operator to be a minus instead of the plus, type it into the calculator, we get about 0.312. Okay, this is all the math that needs to be done. These are the max and min of our confidence interval. So step 5, I'm going to scroll back up, write a statement. Step 5. We are 90% confident that between what? Well, between 31.2% and 36.8% of teens text while driving. And that's it. We're done. So just to recap what we did. We went out and sampled 800 teens and found that 272 of them admitted to texting while driving, which that corresponds to about 34%. 34% of teens text while driving. And that's what you're going to hear in the news. 34% of teens text while driving. But we realized that this 34% is not an end-all be-all, because we only talked to 800 teenagers and only 272 said yes. If you go out there and you get a sample of 800, you might have a different amount that say they text while driving. So you might not get 34%. And so we're going to try to construct this range that kind of accounts for all that variation. So our estimate is 34%, but after some fun math, that's all this, we say, okay, we think it's 34% based on our sample, but we really are going to be safe here and say it's between 31 and 36%. Well, 31.2 and 36.8% of teens text while driving. Now, the question is it possible that the true proportion actually is outside this range? Is it possible that the true percentage of teens that text while driving is, let's say it's outside this range, let's say it's only 30%. Let's say it's down here somewhere on our range. Is it possible? Of course, because we are only 90% confident in this range. We realize there's 10% of us that realize okay, well, this range might not actually capture the true proportion. It could be outside of this. We're pretty confident it's in there, but there's definitely a chance that it's not, right? All right. Especially because if you think about it, it's only 272 of them admitted to texting while driving, right? So it's totally possible we are underrepresenting how many teens text while driving. So this 90% confident thing, I don't want you guys to forget. We're not 100% confident that the true proportion is in this range, but we're pretty darn sure. And now is normally the time I get a question, well, is there a way to be 100% confident? And the short answer is no. There's no way to be 100% confident in a range at all. You can be 99.9, but you're never going to be 100% confident, because the only way you can be 100% confident that your range captures the true percentage is you would say, well, I think the percentage is between 0 and 100. That's the only way you can be absolutely sure your range has the true proportion of teens who text while driving, is by covering every single number. Oh, I believe it's between 0 and 100%. Well, that doesn't really tell us anything. So that's why 100% confidence intervals aren't a thing. Whereas 90, 95, 99, those actually work out to be a little bit more strict of numbers. And so now we have to ask ourselves, what would happen to our interval if we increase our confidence to be 95% confident? So what would happen? So currently, our 90% confidence interval was between 31.2 through 36.8, right? And I'm going to draw that maybe on a number line, actually. Say 31.2 through 36.8. This is 90% confidence right here. What if we want to be more confident that we actually do capture the true range, or the true proportion? If we want to be more confident, we're going to have to include more numbers. If we want to be more confident, maybe take it down some, right? So that we still capture how confident we were at the 90% level, but then some. We'll go a little bit more in both directions. If you want to be more confident, you got to cover more numbers. And if you were to decrease your confidence, take it down to 80%. Well, if you're going to decrease your confidence, you can cover fewer numbers and cover something inside here. If you want to be less confident, you can hone in. But if you want to be more confident, you got to expand outwards, right? You want to be more confident in your range, you're going to have to include more numbers, more possibilities of what the true proportion is. All right, now would be a good time to go try some practice problems on creating confidence intervals for proportions. There is one more thing in this section that kind of can come up in real life. I really want you guys to understand how to create the intervals themselves. That's really going to be the big thing. Because a lot of you already admitted that you're not stats majors. You're not going to be out there doing the statistics yourself, but there is one more thing in the section that they mention. We can find a sample size needed to construct an interval within a certain margin of error let's call the margin of error E by, if we want to know our sample size, we want to know our N. It's basically solving the confidence interval equation. It'll be P times Q hats times Z sub alpha over 2, our critical value, over the margin of error squared if no prior estimate is known. Use p hat equal to 0.0. Use p hat is equal to 0.5, which would make q hat equal to 0.5 as well, right? If p hat is 50%, q hat will be 50% as well. And that becomes, instead of p hat, q hat there, you can actually simplify it to be 0.5 times 0.5, right? If you don't know what p hat and q hat are, you can make it 0.25 there, because that's what 0.5 times 0.5 is, times a critical value over margin error. And there's some examples of this in the book on page 401 in the book. And so examples like that could come up on group assignments and stuff, but on quizzes, I'm definitely, I can already let you guys know, I'm going to be more interested in the actual creation of the interval. Something like this example right here, where you have to go through the steps of creating the confidence interval for proportions, and then report it to me with a statement. And always keep in mind that that range is not an end-all be-all, that you're only 90% confident or 95% confident that range contains the true proportion. So I don't want you guys to think, oh, well, that's the end-all be-all, because this is still statistics. We still could have made a mistake somewhere. We could have had an unrepresentative sample of the population. Something could have been wrong with the survey itself. You know, how many teens are actually going to admit to texting or driving? So there's all those other things, those unknowns that we talked about way earlier on in the semester that we have to keep in mind. So I don't want you to say this is it. The true proportion is definitely within 31.2 to 36.8. No, we're only 90% sure that it is. Well, actually 90% sure that the process worked. All right, so that is all for confidence intervals for proportions. I will save these notes as a PDF as well and post this recording to Blackboard. If you have any questions, make sure to email me or come into office hours or anything. I hope this worked. If you find any mistakes within my notes, because I am human, of course, reach out to me, let me know, and I'll definitely make a correction if there actually is anything wrong, or if you're getting stuck anywhere. I will post more practice problems like this example here on Blackboard as well, and there are other videos from another instructor who's taught statistics at CCBC posted there as well. After this video, we will move on to 9.2, which is confidence intervals for means, which actually follows a lot of the same structure. So hopefully you get good at this first, and then 9.2 will be a lot easier. All right, that's all. Thank you.